All right, guys, today we're going to be looking at the rational root theorem on the way to finding all the zeros of polynomial functions. We'll talk a little bit more about that in just a second, but this is going to be a culmination skill of sorts. So if we started out, let's look at a polynomial here. Let's examine this. 3x plus 1, 2x minus 1, x plus 2, x minus 3, 5x minus 1 equals 0. Okay? What are we looking at? What is this?
Numbers, parentheses, x's, variables, confusion.
In algebra terms, what are we looking at? A factored out fifth degree polynomial. Zach's right. It's a factored fifth degree polynomial. We have 5 linear terms, right? 5 first degree terms would multiply together to give us a fifth degree polynomial. All right. What are the roots of this fifth degree polynomial? Because it's in factored form, we can find the roots pretty easily, right? What are they? Negative 1/3, positive 1/2, negative 2, positive 3, and I'm writing these in this way for a reason, and positive 1/5. Those are our roots, our zeros. They're all rational numbers, and the reason I wrote them in fractional form is just because I wanted you to show that they're actually rational numbers in fraction form. Because the rational root theorem deals with how to find rational numbers, rational roots, the rational ones. Okay, that's why it's called the rational root theorem. Rational numbers are numbers that can be written as a fraction. All right, now, what was this polynomial before it was factored out? A fifth degree polynomial. What was it? Does anybody want to multiply those 5 factors together and tell us what it would be? All right, we know Payne says right out of the blocks that our leading term would be 30x to the 5th. How'd you get that, Payne? 3x times 2x times x times x times 5x. That gives us 30x to the 5th. Does everybody agree with that?
You can just multiply all the denominators.
All right.
That's much easier.
You're on to something. It's not always going to work, though. Plus, who cares what's in the middle? For now, we don't care what's in the middle. What's our last term going to be? Negative 6. Equals 0. All right, so our original polynomial was 30x to the 5th plus something times x to the 4th plus something times x to the 3rd plus something times x squared plus something times x minus 6 equals 0. Now, we do not have the factoring skills needed to solve 30x to the 5th. Fifth degree polynomials. We don't have the factoring skills necessary to do that, right? So we're going to have to find a different method for solving a fifth degree polynomial. There is no formula for a fifth degree polynomial. I've alluded to that before in class. So we're just down to analysis of the function and the rational root theorem. Now luckily we already know all 5 rational roots of this polynomial because I gave it to you in factored form. Now, but can we see a relationship between our roots and our original function? Drew already pointed something out. What did you point out, Drew? These denominators multiply to equal what would we call 30?
Coefficient.
It's which coefficient is it? The leading coefficient. It's the leading coefficient because the polynomial is in standard form. The leading coefficient is the coefficient of your highest degree term, your fifth degree term in this case. So all of my denominators are factors of 30. What about the numerators? The numerators are all factors of 6, right? Negative 6 in this case. If you multiply them together, you get 6. But the point is that they're all factors of negative 6. What are the factors of negative 6? Plus or minus 1, plus or minus 2, plus or minus 3. Those are the possible factors of a negative 6. And we see that all of our numerators are factors of the constant term. Y'all listening to me? The numerators are the factors of the constant term of the polynomial, and the denominators of my rational roots are factors of the leading coefficient. Okay? It's easy to see this in a concrete example in just a minute when I give you the rational root theorem. Hopefully it'll make a little more sense because of what we've looked at first here. Okay? A couple of other very important skills for us today are these warm-up activities. Have a look at this. Warm-up activities. Number 1, solve x squared minus 4x plus 2. Justin, how would you solve x squared minus 4x plus 2? It's called what? What does he describe and call? Completing the square. Yeah. Why is this one easiest to solve by completing the square? A is 1 and B is even, right? So, again, every problem that we're going to solve today and tomorrow and next week that we're going to graph is always at some point going to involve solving a quadratic. So, this particular one, you could use the quadratic formula, but the easiest way is to complete the square. So you move the 2 over, make it negative 2. Half of negative 4 is negative 2 squared is positive 4 to both sides, right? And then, so on the left, we'll have x minus 2 squared. We've completed the square equals 2. And then plus or minus the square root of 2. You don't really, probably some of you don't even have to show this step at this point, but then you add 2 to find the 2 irrational roots. X equals 2 plus or minus the square root of 2. Now there are some facts and things related to irrational solutions. They tend to always be what? Because it's always plus or minus there, the irrational roots of a polynomial with integer coefficients are always conjugates. Okay, so 2 plus the square root of 2, 2 minus the square root of 2, they're going to always kind of be conjugate pairs, just like our complex solutions are. All right, what about number 2? We want to see if it'll factor, right? We didn't even really need to see if this one will factor. There's no factors of 2 that give us negative 4. But to see if this will factor, 2 times negative 5 is negative 10. 5 times negative 2 is what we're looking at, right? So to factor this would be clearly 2x and x. And we need the inside and outside terms to be 5x minus 2x, which means this term over here needs to be negative 1, and this term here needs to be positive 5, and that gives me negative 5, so I'm good to go. All right, so the 2 roots there are negative 5 over 2 and positive 1. All right, is everybody with me? Just quadratic techniques. Test 4 that I just passed back to you. That test was about all the techniques that the only thing we didn't practice today is the quadratic formula, and we'll have some exposure to that tomorrow. You know, just kind of reminding you how to do that. What about number 3? How would we determine whether the given linear expression is a factor of the given polynomial? In other words, how would we determine if x minus 3 is a factor of this polynomial expression? Divide and see if the remainder is 0. How do we know if numbers are factors of each other? You divide. If there's no remainder, then it's a factor. So synthetic division is certainly the slickest way to do this one. The root of x minus 3 is 3. All right, so we'll do 3. And then we're dividing x minus 3 into 1x cubed minus 2x squared minus 5x plus 6. Skip a line, draw a line, bring down to 1. And we're going to see if it is, right?
I love the synthetic division. So aesthetic.
All right. 3 times 1 is 3. I'm not real sure what you just said there, buddy, but
Aesthetic. All the numbers are in a straight line.
it's aesthetic. 3 times -2 is aesthetically pleasing.
Yeah.
Okay. So we get a 0, which tells us what? Yeah, 3 is a root, and x minus 3 is a factor. As a matter of fact, this polynomial that we started with is equal to x minus 3, this is important, times what? X squared plus 1x minus 2. Where did we get that from? 1x squared plus 1x minus 2. Now we could further factor this. Now we're on to something, right? X plus, that's not what this problem is telling us to do, but I'm just running with it now. What have I found there? All 3 linear factors and all 3 zeros of that cubic polynomial. And I found it just by finding 1. All right, that first 4-term polynomial is not factorable for us. We can't factor it the way we would like to factor 4 terms. It doesn't factor by grouping, so we have to do something different.
How'd you get that x squared plus x minus 2?
Okay, when you divide x minus 3, right? That's what we're doing right here in this step. We're dividing by x minus 3. The dividend is, the quotient is x squared plus x minus 2. Okay? All right, number 4. Is x plus 1 a factor? Let's see. We got to use the root, right? The root of x plus 1 is -1. If we're using synthetic division, we always use the root. Skip a line, draw a line, bring down to 3, multiply and add. -3 gives us -7. That gives us +7. We can just about stop right now. It's not going to work, is it? -1 is not a 0, which means x plus 1 is not a factor. Okay? All right, so that's just some skills that kind of tie things together, what we've done the last day or two. Amara?
So when would it be better to use long division?
Only if you're forced to.
Okay.
In this case, if you're just trying to, Amara, if you're just trying to determine if it's a factor, I would always use synthetic division. If you're actually trying to find the quotient, I would only use synthetic division if we have a linear factor with a leading coefficient of 1. Okay? A linear divisor with a coefficient of 1. All right, so zeros of polynomials. What we're going to do today is use the rational root theorem, and this all the stuff we've done up to this point, these first 13 minutes of the lesson, have all been just kind of warm-up things that we've been doing in the previous days and weeks that are going to be useful to us in this lesson. What we're doing today is using the rational root theorem to find the zeros. What's another word for zeros? Roots, solutions, x-intercepts. So we're finding the x-intercepts, roots, zeros, solutions of polynomial functions. Now we've not reviewed what we mean by polynomial function in quite some time. A polynomial function is a function, y'all listening to me? It only has whole number exponents. Whole number exponents. What are whole numbers? The counting numbers, right? 0, 1, 2, 3, 4, 5. In other words, no negative exponents, no fractional exponents. All right, so we can't have any square roots in our equations. We can't have any variables in the denominator. That would be where we get negative exponents from. So this is good old x to the third, x to the fourth, x to the fifth polynomial functions. Okay, so the rational root theorem is a new theorem for us today. We alluded to it in that first little warm-up thing that we looked at. But here's what the rational root theorem says. Let P, capital P, be a polynomial function with integer coefficients in standard form. Stop right there. Write that down. Stop right there, and let's talk and make sure you understand all the conditions. This is the conditions. They're giving us the conditions that we're working with. We're working with a polynomial function that has integer coefficients in standard form. Yeah, that'll be fine. There's a podium right behind you there. You can stand. Okay, what do we mean? We just defined polynomial function again, right? It's x to the fourth, x to the third, x to the fifth, x squared. What do we mean by standard form? What is standard form of a polynomial function?
Standard form would be like, what is in the x to the fifth, in degree form.
The degrees are going down in descending power, right? So it's the highest degree down to the constant term. That's right. So that's what standard form means. Integer coefficients, that's like plus or minus 1, plus or minus 2, plus or minus 3, all of our integer values. So I don't have any coefficients like 2/3 or square root of 7. You know, if we start getting into irrational or complex coefficients, then this theorem doesn't apply. There's different theorems that apply to those things, but none that you'll study in high school or maybe anywhere else for that matter. But so we're dealing with nice polynomial functions. If p over q, now that's lowercase p. I want you to make sure you understand that this p is not that p. They're not related to each other. If p over q, we don't really need that, is a root of p of x equals 0. Okay, now this capital P and this capital P are talking about the same function. We just have one in function form there. In other words, if p over q is a root or a 0 or an x-intercept of that thing, then here's what we know. Based on that example that we did at first, little p has to be a factor of the constant term of p of x. What do we mean by constant term?
The last term without a degree.
It's the term without an x. Yeah, no variable. Right. And q, what do we know about q? No, q can't be 0. Q is a factor of the leading coefficient of p of x. Now, I can't recall what our polynomial function was that we had on the board a minute ago, but wasn't it something like, was it 30x to the fifth? 30x to the fifth, and then it was plus a bunch of stuff in the middle, plus 6, minus 6. And what were our roots? Tell me what those roots were.
3, 5, no.
Negative 1/3, 1/2, negative 2, negative 3, and positive 3. And what? 1/5. I'm not as concerned about these being accurate at this point, but what I want to show you is that all of these denominators are factors of what? 30. All these denominators are factors of 30. Okay? All the numerators are factors of negative 6. That's the rational root theorem. Okay? If it has a rational root, if it has a rational solution, then it will always fit that description. The numerator will be a divisor of a factor of the constant term, and the denominator of our rational solution will be a factor of the leading coefficient. Always. Okay, now let's just dive in and have a look at an example. Okay, I want us to find all rational roots of 8x cubed plus 10x squared minus 11x plus 2. finding all the rational roots. Actually, we're going to find all of them, whether they're rational or not. But we're going to start off by finding a rational one, because we don't have any algebraic methods for this. There is a cubic formula, but it's not very user-friendly. It would take a lot longer to do that. We could solve it graphically, but we're doing an algebraic solution. Right. So step one is going to be to make an organized list of all the possible rational solutions. Right? I want to make an organized list of all the possible rational solutions. If there is a rational solution, that rational solution is going to be the factors of 2 divided by the factors of what? Divided by the factors of 8. What are the factors of 2? Plus or minus 1 or plus or minus 2. It's good to be as organized as you can on these, because they can get a little bit it's easy to miss them if you're not meticulous about being ordered. All right, what are the factors of 8?
2.
Plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. I'm going to write these up top. You don't have to write these where I'm going to write these in my notes, but I'm just going to leave room at the bottom here. Okay, so our possible rational zeros are the factors of 2 divided by the factors of 8. So it's all the different fraction combinations I can get from these numbers. All right, so let's just take 1, and let's list all the fractions that would have 1 as a numerator. What are they? Plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4, and plus or minus 1 over 8. That's a lot of possible rational zeros, and I haven't even gotten to 2 yet. But the good news is that when we're dealing with the 2, we're going to get a lot of repetitions, right? As a matter of fact, I think that plus or minus 2 over 1 is the only thing that's not a repetition, right? Because 2 over 2 is 1 again, right? 2 over 4 is 1/2, and 2 over 8 is 1/4. All right? So I don't really even need to list those again because I've already got them up there. Okay, so what have I created here? These are the list of all possible zeros or roots, right? How can I determine if any of those are roots? Do what?
Plug them in.
Plug them in? Yeah? Is there a quicker way?
Multiply them all the denominators together.
Synthetic division.
No, there's the other stuff.
This is the quickest way, I promise. And it gives us some other useful information, right? If we're not using a calculator, this is the quickest way to come up with these values. So bring down to 8, multiply and add. That would give us 18. It gives us 18. It gives us 7. That gives us 7. And that gives us 9. Right? Is 1 a 0? No, it's not. Okay, so it's not a 0, but we're not doing this at this point. What have we generated here? What have we shown? We've shown that 1 is not a 0. X minus 1 is not a factor. But we've generated a point, right? I could put that point up here, 1, 9. Because that point is going to be useful next week, Tuesday and Wednesday, when we're sketching the graphs of these things. I can use that point. And that comes from the remainder theorem. Okay? All right, what would I do next? You skipped ahead to 2? Does 2 work? Oh, you don't know. All right, here, let's do this. Let's do -1. Let's just kind of go through our motions here. Now, 2 I would try next just because I'm avoiding fractions for now. You know, sometimes fractions aren't avoidable, but always try the easiest ones. And generally in is -1 a 0? It is not. It does give us a point. I can put that on my list here. When x is -1, y is 15. You'll get to where you can kind of start looking at some things here that are going to work. Do you think that 2 is going to work? 2 balloons quickly, doesn't it? What does 2 give us? 16, 26, 52. No way that's going to work. Right? What about -2? This just takes a minute, right? We're looking for possible rational zeros. What does that give us? -16. -6 times -2 is +12. That gives us a 1. It does work, doesn't it? Okay. That's -2. Boom. 0. Well, it's the only one that we have to find this way. Now, we could continue this process until we found all 3 of them, but the problem is it may not have 3 rational zeros. It may only have 1 rational zero. This may be it. Okay? But what have we gotten here? What have we found? We found that -2 is a 0. X plus 2 is a factor. Okay? As a matter of fact, our original polynomial is now 8x cubed plus 10x squared minus 11x plus 2 is equal to x plus 2 times what? 8x squared minus 6x plus 1. So I have used the 1 0 that I've found to get a factorization. Now, using all of our skills from test 4 that we just took, I'm going to be able to easily find the zeros of that polynomial. Now, look, this process is too long and too intense to daydream. Y'all stay with me today. Is this factorable? Are there any factors of 8 that add up to be -6? -4 and -2. So what I'm looking for here is -2x and -4x. So it's pretty clear I'm going to use 2x times 4x to get 8x squared, right? And what do my 2 constant terms there need to be? -1 and -1. If I did that last little in check, -1 times -1 is +1, which is what I had there, and that's a good factorization. Okay, so that means that my 3 roots are -2, which I found by synthetic division, +1/2, which I've found by factoring, and +1/4. All right? Yes, sir.
Whenever we're doing synthetic division, you just suggest doing whole numbers if we have them?
I start with the whole numbers. Yeah. Now it's really not a disaster to use the fractions if you have an idea that one of the fractions are going to work. Now, for example, if we wanted to, we could go back to this and we could check any of these roots that we found to make sure that they work. If I put 1/2 here, bring down to 8, that would be 4, that's 14, that's 7, that's -4, half of -4 is -2, and you get a 0. It's going to work. So if you had the foresight to check 1/2 first, you would have found a 0. Now, but then it becomes a little bit more difficult. If 1/2 is a 0, that means 2x minus 1 is a factor. This is not actually the quotient, but it's going to have the same zeros as the quotient would. Because all those are even, you can divide them all by 2 and have a quadratic that's factorable again. All right. As the quotient, if you were actually trying to find the quotient, yes, you would have to divide it by 2 to get the quotient. And that's one of the reasons that I told you not to use synthetic division unless your divisor is a linear coefficient with a linear term with a leading coefficient of 1, because it's a little bit tricky to actually get the quotient. But the actual quotient and this quotient have the same zeros, so you're still in good shape. Okay? All right, so y'all see what we've done. Now looking ahead to next week. Tristan, you with me? Looking ahead to next week. What have I found right here? 3 x-intercepts. What did I find along the way? 2 points there. What's the y-intercept of this graph? If you let all your zeros, x be 0, y equals 2 is the y-intercept. So that gives us 3 x-intercepts, a y-intercept, and 2 other random points. I'm going to be able to get a really good sketch of my graph using those points.
Do you need those 2 points though?
Yeah, they're pretty helpful. They're pretty helpful.
Say if you got like the factor in like the first try and you didn't get those 2 points. What do you
Yeah. Now, you'd still be able to get a good, accurate sketch of the graph if you're familiar with what a cubic function looks like. And we'll talk about that along the way next Tuesday or Wednesday. Okay? So the answer is no, you don't have to have them, but it's helpful. It gives you some idea what you're doing along the way. All right? So let's have a look at another example. This is going to be the last one we get to today. You with me, Drew? All right. The first thing we're going to do is use the rational root theorem to determine the possible rational zeros. Now, the rational root theorem, again, let's be reminded, tells us that if there is a rational root, it's the factors of this number divided by the factors of our leading coefficient. Well, luckily, our leading coefficient is 1. Okay, so I'm not going to have very many terms to deal with because I got a 1 here. Excuse me. I'm not going to have any fractional terms to deal with because my only denominator is 1. So my possible rational zeros are just the factors of 12. Plus or minus 1? Yes. But because it has positive and negative factors, it's not a... We're not as concerned about the sign of that number. Plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12.
So because that's 1, you only have to find the factors for the 12.
Right, all over 1. You know, there's nothing else. There's no interesting. Our leading coefficient is 1, and so the only thing I could put in a denominator is 1. So I've got all integral rational zeros, possible rational zeros. All right, so what will we get if we just start chugging and plugging, right? Plug and chug. Put test 1, 1x cubed, 4x squared, negative 6, negative 12. Skip a line, draw a line, bring down to 1. We're testing to see if 1 is a 0. That's 1, that's 5, that's 5, that's negative 1, that's 1, that's negative 1, that's negative 13. It's not a 0, but we generated a point we can use on Tuesday or Wednesday when we're graphing these things. 1, negative 13 is a point. Y'all with me? Has anybody gone ahead and found one somewhere? 3 is a 0?
No.
3 is not a 0. Okay. You got me all excited there, Payne. Well, let's just go on through. Has anybody done negative 1 yet? It's not going to work, is it? But it does give us another usable point that, we could say, all right, -1, -3 is a point on the graph. What about 2? Does 2 work? Tomorrow when we work on these in our groups, I'm going to give you guys whiteboards so you can kind of erase and do this. What I'm doing. Does 2 work? Two works, doesn't it? All right, so we found a 0. What else have we found? If we find a 0, we found a factor, right? If 2 is a 0, then x minus 2 is a factor. As a matter of fact, q of x, our original polynomial, is equal to x minus 2 times what? X squared plus 6x plus 6 equals 0 is what I'm looking for. See how we use this first factor that we find, and now we're left with a quadratic here. What's the best technique to use to solve that quadratic? Completing the square is what I would use because a is 1 and b is even. You could use the quadratic formula. It's going to work. It's just going to take you a little extra time. So if I come off over here to the side and solve x squared plus 6x plus 6 by completing the square, I'm going to say x squared plus 6x equals -6, right? What am I going to add to both sides? Half of 6 is 3, and 3 squared is 9, right? So I'm adding 9 to both sides, and that's going to give me x plus 3 squared equals 3, which means x plus 3 is plus or minus the square root of 3. With me, Zach? Yeah? Subtract 3 from both sides, we get x equals -3 plus or minus the square root of 3. To what kind of solutions? Irrational solutions. So my 3 solutions are x equals 2, x equals -3 plus or minus the square root of 3. There's my 3 zeros. Now, if I was sketching the graph, those irrational x-intercepts, I could use a calculator to approximate where they are. -3 plus the square root of 3, -3 minus the square root of 3, and +2 are my x-intercepts. What's the y-intercept of this graph? -12 is the y-intercept, and I've got those other 2 points up there that I could use to kind of give me a pretty good idea of what the graph is going to look like. Okay, now this is not the shallow, this is not the kiddie pool of algebra here. We're in the deep end of the algebra pool at this point, using a lot of skills that we've picked up through this semester to solve higher order equations and going. So we're going to stop there for today. What I want you to do is for homework, it's page 361. Just want you to do 2, 4, 6, 8. Who do we appreciate? All right. Now, follow the directions. Are y'all listening to me? The directions just tell you to state the possible rational zeros. I don't want you to actually solve. We'll work a couple of these examples together tomorrow, but I want you to state, not five-tate. State the possible rational zeros is the only thing you'll do with those. All right?